Okay, let's go ahead and get started. Today we're going to cover Module 9, Traveling Salesman Problem. So I have that lecture posted that you can review. Traveling Salesman Problem is probably one of my favorite problems of all time. It really is. I first learned about it when I was working on my master's degree. I remember looking at taking a course, and it was talking about heuristics that you would learn in the course, and I can remember trying to figure out what a heuristic was. And I always remember, if you ever hear the word heuristic, it just means rule of thumb, just a quick kind of algorithm for doing something. So last week when we went over minimum spanning tree problems, that's a really good simple heuristic. You just pick the closest node to you. So if you had to sum it up, you're trying to, create a network, least amount of distance to span the network. How do you do it instead of some sophisticated algorithm? Just say what's closest to me, that sort of thing. So imagine we had a class full of people. We had say 20 people in a class, and I said break up in 5 groups of 4. How do you think that's going to play out? Well, some people, if you know one of your friends and they're in the back, you may go back there and let's work together. But in general, you'll kind of, if you don't know anybody, you'll look at the person beside of you and say, you want to be on the same team? And that's just a heuristic. So that's all that is. And so there's a lot of heuristics out there to solve this type of problem. It is a very, very useful problem in the sense of that there are so many things in the real world that exhibit traveling salesman qualities. In general, they're very hard problems to solve in an optimal manner. So we have a lot of times near optimal approaches that'll give us good answers. I posted one chapter on Moodle pertaining to a whole book that's written about the traveling salesman problem. So when you're looking at the material, you can download that. It's like a sample chapter that came with the, you can get like off Amazon or something. So I just posted it. I don't think I'm breaking any copyright rules because of the Fair Use Act and that sort of thing. But if you want to buy that book, read about it. It's pretty cheap. You can get an e-copy of it. If not, that's okay too. But it just tells you a little bit about the history of the problem. So there's literally a whole little book written on just the traveling salesman problem. Like I said, they're in nature everywhere. Protein folding problems, which is very important. We're just now really beginning to understand kind of how that works. And to be able to model them, and that's important for developing new drugs to fight cancer. So, the next set of hopefully treatments for dealing with cancer is going to be, gene therapy and that sort of thing. And maybe at some point we can get away from chemo because chemo basically just goes in and kills everything. Gene therapy, deals with more of trying to address the individual cancer cells themselves. So it's not unrelated. It is completely and utterly related to what I'm going to be teaching you today. Now, I mean, it's hard because you're dealing with proteins and gene sequences and that sort of thing, and that's very hard. I remember years ago when I applied, one of the schools I applied to for my doctorate had a list of all the programs and your GRE scores you had to get, and I remember looking at the genetics program that this school had, and I remember of all the programs that had the highest requirements in terms of your quantitative math, GRE, and some other score. Quantitative, it wasn't the English that they cared about, but it was the other two that you had to take at the time. So anyway, a little bit of background. So we're just going to jump right in. I'm going to show you how to solve these problems. Like I said, I try to teach in the most applied way that I can. So, I'm going to give you these problems. I'm going to show you how to formulate them, solve them in Excel. But I want you to be aware that the way we're going to be solving these problems is probably not going to give you an optimal solution. Okay? It'll probably give you a good solution, and we're going to look at this, and I'm going to talk a little bit why. But a lot of times, if you have some type of problem like we're going to discuss, what you're wanting is a solution better than what you got. Okay? The technique that I'm going to show you is probably going to give you that, and the longer you let it run, the better it's going to become. But if you run across problems like this in your job, it's kind of up to you to do the research to figure out the best way to solve it. And it's like, well, I thought that's what you were supposed to be doing. Well, it is, but this one topic could require an entire course. I mean, literally, you could just take an entire semester on traveling salesman problem, do a special topics, call it traveling salesman problems, and do an entire semester just on different types of traveling salesman problems and different techniques you could use to solve them. I mean, you can use dynamic programming, integer programming, all dozens, hundreds of heuristics, genetic algorithms, and my goal is more exposure. Okay. So the neat thing about the traveling salesman problem is, I could take my 9-year-old daughter, who's 9 at the time right now. Actually, she's 8. She'll be 9 this summer, and I could sit down and explain it to her. I could say, here's what we're going to do. I'm going to give you the 7 dots, and I want you to start at one dot and finish at another dot, and I want you to connect them in a way that minimizes the total distance. It's like, oh, okay. And she would start drawing, and here's the answer. All right, let's take a look at it. And they've actually researched this. They found that humans do pretty good on just single objective traveling salesman problems, like where you're dealing, say, with just distance. So if I just give everybody a random problem and say find the optimal solution, you're probably going to get within, I don't know, maybe 30% of the optimal solution just by looking at it. You'll just kind of start drawing, and, well, I don't want to cross here, and I'll move here, and this and that. But getting from, say, 30% of the optimal to the optimal could require a lot of work. Okay, and to guarantee that it's an optimal solution, I mean, could require days of computer time. Okay, they've solved this problem for very large instances. Last time I checked, several years ago, probably a decade or so ago, maybe even longer, they actually solved for the entire world. So, you connect all the cities on planet Earth. What's the optimal solution for that? And it took years to solve that problem, but they finally did. And now, what else do you need to know? So what we're going to do is we're going to come in here and we're going to say, how should I arrange these cities? Which city should I start with, and which city should I end with? This is what's referred to as a one-way traveling salesman problem, meaning you start at one city and end at another city. You have a two-way traveling salesman problem if you start at one city and end at the same city. So you're trying to make a loop. So the reason why it's called two-way is then you can go either way, because it's essentially like a circle. You can go one way around the circle or another way around the circle. And once you solve that problem, then your start end city can be any city, because you're always going to pass through that city. So I'm going to open this up in Excel, and I'm just going to start from scratch, just to show you guys how we would actually, do a problem like this. Okay. So what we're going to do is I'm just going to come in here, and I'm just going to start naming, and I give you a relatively small problem. So if I give you a larger problem like an exam, I will give it in a digital format. This is kind of an image, but I'll give it in a way where you can copy and paste, because the goal isn't data entry. The goal is to have you guys working on the problem, but this is a relatively short problem, so I'm just going to plug them in. So here are our x coordinates. Here are our y coordinates. These are just random numbers that I created. Now, like I said, an applied problem that is dealt with every day is UPS. I mean, this is a problem they deal with every day. They have a truck full of packages, and they have to deliver to people. And which way did they deliver? Okay, so what I'm going to do is I'm going to go in and I'm going to calculate the distance. Okay, between each one of these cities. Okay, so the first thing I've got to do is I'm going to put in like a random number here. I'm going to use what's called a VLOOKUP, and I'm going to explain what this does. VLOOKUP. I'm going to look up a value. The value I'm going to look up is value 2, which is just going to be cell F2, comma, table array, which is going to be kind of my information matrix. Okay? And I'm going to go ahead and highlight this and hit F4. And does everyone know what F4 does when you hit it? It locks it, so it makes it an absolute reference. So it puts those dollar signs. Column index. Oops. Column index is going to be 2. Now, why did I pick column index 2? Here's what I'm doing. This is how VLOOKUP works. It says, okay, I want to look up a value of 2. The value of 2 that I look up is in my first column. It's just the way it works, okay? So your first column always kind of has to be your reference column. If you don't like it, sorry, that's how Excel works. I'm going to find the value of 2 in this whole matrix right here, and I'm going to report the value of the second column. So if I change this to a 3, it's going to report 95, okay? See how this, it found 2 and it reported column 1, 2, 3. All right, so I'm going to report the second column here, and then I'm going to come in here and I'm going to copy this and put it here and make this a 3. So basically what it's doing is when I change this number, it's finding where 5 is and reporting these two values. Okay. Now, a couple things. One, you can't have duplicates. I can't have like city 3-3, because if you do, it gets confused. I think it reports the first one. These also have to be sorted. So if they're not sorted, you have to go in, highlight them, and sort on the column you're looking for. So it does have some limitations, but in the context of what we're using it for, it should never be an issue, because all of these are just identifiers. That's it. It's just a reference. You know, city 3 could easily be city 5. It doesn't matter, all right? So that's how this works. So what I'm going to do then is I'm just going to drag all of these down. I'm going to drag them down like this. And it should just be 1 for 1. You know, 1 here, 3149. So all this is thing. If I change one of these, see how it just changes that reference? That's all it's doing, okay? Now what I'm going to do is I'm going to go over here and I'm going to calculate distance between each one of these cities or nodes. And I'm going to say, all right, the way I'm going to calculate this is I'm going to take this x, this x minus this x, we'll square it, plus this y minus this y, and square it. And then I am going to take the square root of this whole function, which is raised to the 0.5 power. So this is just the distance formula that you learned in geometry in 9th or 10th grade. That's all it is. All it's doing is calculating the distance from node 2 to node 1. Then I just come down here and I drag down here. You notice I don't go all the way to the end. And the reason why I don't go all the way to the end is because then I would be calculating from here to here. So if you think about it, if you have 7 nodes, you only have 6 connectors, right? So, I mean, that's just the way it works. If you have, say you have 3, 3 points, 1, 2, 3, you only have 2 lines between it. So that's why you only have 6 distances. So now what I'm going to do is I'm going to come in here and I'm going to hit sum and sum up total distance right here. Now, just for the heck of it, I'm going to come in and I'm going to create a little graph so we can look at this. And I'm just going to create a graph, a scatter plot that looks like this. And then I'm going to go ahead and make this larger now since we've already, and I'm just going to delete this so it gives me a little bit bigger. Okay? So what it does is it just goes city 1 to, so if I put something like, randomly, let's say I put a 3, a 2, and a 1, something like that. See how it just, it shows you what's called the tour, okay? So what I want to do is I want to figure out a way, I can go 7, 5, 6, 2, 1, 4, and whatever's left, 1. That's a valid tour. Does it look optimal? Probably not. But this is how I create the problem, okay? So what I want to do is I want to go in and I want to figure out how I can use some type of, in this case it's going to be a genetic algorithm, but model building to get Excel to put these numbers in the order that minimizes the total distance. So I'm going to go up here to data, I'm going to go to solver, and this is kind of I'm going to refer to it as an atypical way to program Excel. I often use tricking. You're trying to trick whatever algorithm it has to move things around in a way to give you the best answer. Okay? So how are we going to do this? Well, we want to minimize this distance. Does everyone see that? Does that make sense? Just minimize this distance by changing these decision variables, and I go down here and there's this option that says DIF. What that is is what's referred to as an all different constraint. What it means is, let's see what I do, make sure I've done this correctly. Must include only variable cells. Alright, what did I do?
You didn't specify what variables to change.
There you go. I'm sorry. Yeah, thank you. These are my decision variables. Thank you. And now I'm going to go down and make these all different. Okay? And that's all there is to it. So formulating one of these is one of the easiest formulations you will ever see. Okay. Now when we solve it, you're going to see it's not going to take a long time because this is a small problem. But this is literally one of the easiest formulations ever. This is it. You're done. You just change these cells, make them all different, set your objective function. We're going to go down and make it evolutionary. Okay. Now the great thing about all different is it automatically forces them to be integer and they have to be all different. So all that's kind of built into that constraint. We go in, we hit solve, and boom. See how it's working down here? So you see that it's already found the optimal solution. It's just converging. There's a parameter in the actual genetic algorithm that says we'll try, and then if you don't find a better solution after X number of seconds, stop. Okay, so that's what's actually happening. So it is actually it's found probably the optimal solution. Now, if you work on really big problems, what you'll see is over time you'll see this incumbent. It'll go down, go down, go down, go down, go down a little bit, and then it'll finally converge. So I may just end up stopping it here in just a second. I'll just stop it, and it says it's paused, and I'm going to say, okay, stop, keep the solver values, and that looks like a an optimal solution to me. Looks pretty close. So if you go under here under options, you'll notice under evolutionary, see how it tells you like maximum time without improvement, population size, mutation rate, convergence. These are all parameters that kind of control the genetic algorithm. All right, so that's why it would go. It'll find it'll find a good solution, and then it keeps grinding through. And if it doesn't find a better solution within 30 seconds, then it stops and says this is the best solution I found. You could make that 2 hours if you wanted to. If you had a larger problem, you can just let it grind through. But what I want you to see is how you formulate one of these. Okay, so I've had run across problems in the past where I've had to use this, and I know the specific problem that I was working with, that I could probably find a truly optimal solution by going in and creating a linear program or maybe an integer program. But it's like, well, that's going to take me a while because I've got to go in and set all these bounds and these constraints and everything. I'll just set it up using a traveling salesman, even though it's non-linear, because I'm looking for a good answer. I'm looking for something. I want to solve this problem in 10 minutes, get it over with, and have an answer that's, within 1% of the truly optimal solution. So I actually go back to using TSP formulations quite a bit for problems that I've worked on in the past, simply because it's a very quick formulation, okay? But be aware that finding a truly optimal solution using this technique many times is very hard, okay? So does everyone understand that? Is it clear? Okay.
This is a one-way, right?
This is one way.
Points,
Right.
and if you do it two-way, is it the same?
Yeah, you want to say how you do it two-way?
Yeah.
All right, here's how you do it two-way. You trick it. It's all about tricking. You come in here and you say, let's let the ending city be the starting city. Just like this. All right. It's really simple to do this. So this is my ending city, right? And then I just drag this down right here, add one more distance, hit sum, add this distance, just like this. I'm going to go in, make me a new graph here, just easier to do than trying to modify it. And have all of these. Insert, and there you go. That's all there is to it. So now do you notice that the one-way solution doesn't appear to be optimal because we've got crisscrosses? So if I go in and solve this now, I don't have to change anything because I've kind of tricked this and just said, well, once I get to the end, let me go back to the beginning. So I don't have to add any more decision variables. And when I solve it, it probably found an optimal solution very quickly. Maybe not. Let me go in and reinitialize this. Sometimes you have to do this with these types of problems. Okay. And solve it. See how it's grinding down? It's a
So it's all about splitting the starting points in the beginning and in the end.
right. It's just basically, and a lot of times that's what I try to emphasize about model building is you may have this problem that you're trying to go in and solve, and it just seems like, well, how would you do that? Or, it's hard. And it turns out that there'll be the simplest, like if you kind of take a backdoor approach, you can find sometimes the simplest way to solve what seems to be like a complex problem. So you always have to be aware of those. And so here is an example of it not finding, after grinding through, it's close. So what you would probably do is you'd probably switch this. So I'd go from like here to here and then here to here. So it's like, well, why didn't it find the optimal solution? Well, it kind of got stuck in a local optimal solution is what ended up happening here. And it's like, well, I don't want it to do that. It's like, I know, but that's the risk you kind of run into sometimes when you're using this approach. Okay, let's go in and let me like switch this around and see if I can work through and get it to. For some reason, it's finding that it's converging on this. I'm pretty sure I have it formulated correctly. And I don't know. A lot of times when it, for some reason, let's see, it's going from 0.5 to.
Why did you leave off the y variable? The y,
Oh, you know,
the y coordinate.
We just use the X.
oh, that's an excellent point. Thank you. I'm sorry. I put it in. That is the problem, I think. You're talking about right here?
Yeah.
Yeah, I think that will fix it. Maybe.
I think we got a bigger number.
Well, that's because this is 0, so 6 to 0 is very small. See that? Let me start it over. So if I make this like a F2, okay, I am doing something wrong. Let me get this straight. Now let's try it. Let's see. 7, 5, 6, 4, 3, 2, 1. Okay. So that total distance is 1100. F2 through F8. I shouldn't have to change that. Minimum. Okay, let me make sure real quick. I2 through I8. Now wait a second. F2 through F8. Okay. Yeah, that's correct. And hit solve. It makes me think.
Shouldn't you include F9 so that it knows to go back through in the code?
No, you shouldn't have to. And the reason why you shouldn't have to, let's see, this is 0.6, this is 0.7, and then 7 goes back to 1. So I should be able to um, 6 to 7, and then 7 to 1. No, 7 7 it seems like I'm doing something that's just very subtle that I don't quite. Let's see. So I go from 0.6 back to, okay, hold on just a second. 0.6 to 0.7, 212. I almost feel like that I'm getting the right answer. It's just I've done something wrong with the chart. Let me go in here and just put these in and see. Oops. 212. Okay, and then 6, this is 0.1, this is 0.1, and this is point. So that is the optimal solution right here.
You made 2.1.
Yeah, let me do this. I think that
It's like the best solution is wormhole.
there we go. What happened? You know, and I don't like making mistakes in class, but in some ways it kind of shows, you know, the struggles that I go through. Also, is I had it formulated right, but what happened was I didn't. I must have had the wrong like points or something. So it was giving me the right answer, but the way I was graphing it wasn't representative of what the answer was. So let's go through. I should just quit while I'm ahead and say, yeah, that's the problem. But I got to be honest with you guys and with myself. And let's go through and see what happens. Okay, so yeah, there we go. Okay, so it was finding the right answer. And, like I said, I don't like making mistakes. I'd rather just go ahead and get it right and say, hey, okay, this is how you do it. But my point is this is actually a good experience, because a lot of times you'll do things and you're just not,
You don't know what's your mistake.
you may be right. So in this case, 703 is the right answer, but what I was graphing, showing the tour, wasn't representative of actually the problem I was solving. So sometimes, it's a sanity check, that sort of thing. Okay? So everyone kind of understand this, all right? All right, now the thing about the traveling salesman problem, the reason why it's such an important problem in mathematics, if you could solve this problem, if you could come up with an algorithm that would solve this problem in what's called polynomial time, all right, you'd be a millionaire. Literally, I mean that. There's a prize out there right now for anyone that can solve this problem and prove that you can solve it in what's called polynomial time. Meaning that, if you have 10 nodes, that adding a node takes let's suppose having 10 nodes takes 10 squared iterations. And if you add another node, adding 11 takes 11 squared, or 11 cubed, or 11 to the 108th power, whatever it may be. The problem is all known algorithms to solve this are what's called exponential time. So it's something like, if you were just to enumerate all the possible combinations, it's n factorial. So if you have a problem that has 10 nodes, you have to go through 10 factorial solutions. It's like, okay, I got a fast computer. It's like, but if I add one node, that turns into 11 factorial, which is 11 times larger. It's not like twice as big. So then it's like, well, okay, yeah, but I still got a fast computer. We'll add 12 nodes. And then now it's 121 times larger. So the largest that's ever been solved, through enumeration, is 27, which is nothing. I mean, 27 is not a problem at all. So that's why these types of problems can be somewhat difficult. All right. But what they found is if you can solve one, you can solve them all, because you can transform any traveling salesman problem into any other traveling salesman problem. All right. So here is an example of that. Let's take a look at this problem. A group of 16 fraternity members decide to go on a road trip. They're going to drive to Washington State like me and my friends did back in 2003. Okay? It's agreed that 4 cars will be taken on the trip. They decide to pair off in groups of 4 to travel in each vehicle. Each member has their own preference about how loud they like music in the car, what the temperature should be, and how often to stop the vehicle. So personally, I don't like a lot of noise. I don't want it too hot or cold, just kind of whatever the ambient temperature is outside, maybe air conditioning to knock off the humidity. And once I get going, I don't want to stop. Just hammer down and go, okay? Someone like my wife, she likes it turned up. She doesn't like to stop that often, but likes it a little colder than what I do. Someone like my mom, she likes to stop every 30 minutes to fill up on iced tea or something, you know. So we have to take these 16 people and put them together such that we create a model using the following data that will assign each student to a vehicle using some metric that will maximize everyone's happiness or minimize everyone's dissatisfaction, ever how you want to define it. Determine what students should travel in what vehicles. So these types of problems are a little bit more subjective. How do you define satisfaction or happiness? I don't know, but come up with something. So if I gave you a problem like this, I'm pretty open to what you give me, as long as you formulate it and kind of justify your answer. So let me explain what I did. Okay? What I did is to create a metric, okay, that that calculates kind of the variance of each one of these. So what I did is I assigned 4 cars, and I say, all right, you know, car number 1, this is a 113. Car number, or person number 2, I should say student number. I said car, but I meant student here. You know, this is 1, 2, 3, 4. So take student 4, for instance. He likes the music loud, he likes it hot, and he likes to stop a lot. Okay? This person right here, they like it quiet, they like it cold, and they don't want to ever stop. Okay? So do you think these 2 people would travel well together? No. Okay? So there's no absolute metric where I can say, you know, where we say, well, let's try to make everybody a 2 or 1.5 or something like that. Here's what I do. I come in and I use standard deviation. Okay? So if you've had my statistics course, you know what standard deviation is. It is a metric, a measure of variance, okay, of how much deviation there is amongst numbers, okay? So in this particular case, this is a 1. So let me go in here and let me type in like 4 ones or 5 ones. And I'm going to come over here and I'm going to calculate the standard deviation of this. You notice it's 0? What that means is there's no difference. They're all exactly the same. How about if I come in and put all 2s? If I put all 2s, what's the number going to be? 0. Exactly. So it's not a measure of the absolute number. It's a measure of how much difference there is. So if I come in and put a 1, 1, a 1, a 1, a 3, a 3, and a 3. You see this number? What does that mean? It's relative. So it's like, well, what does 1.095 mean? It's like, it doesn't mean, it just means that it has a standard deviation of 1, which you can turn into a bell curve, and it does have some meaning. But what's important is that it's a number larger than this, or it's a number larger than this, okay? So it's a metric of how different we are. And the assumption that we're going to have is that the more different you are, the more unhappy you're going to be. Okay, maybe not. Maybe I don't like loud music, you like loud music, but I did say fraternity, right? Let's suppose it's a fraternity and sorority. So she doesn't like music loud, I like it blasting, but I'll settle just so I can ride in the car. You know, I'm trying to get a date or something like that. But what we're going to assume is that, no, this is the metrics we're using, okay? So does everybody understand why I'm using standard deviation? It's really, the way you'd calculate it is you'd take the mean of these and subtract each one of them and square them and add them up. So the reason why you square them is because it turns a negative number positive. So you're always adding positive numbers. So what I did is this. I went in and I said, I'm going to calculate this for 4 different cars. And I colored them different colors. And I said, I'm going to calculate a standard deviation. I'm going to calculate 3 standard deviations. The standard deviation of music, the standard deviation of temperature and the standard deviation of how often you want to stop. And I'm just going to add them up. All right? So if you ask me, well what does this number mean, 2.915? It doesn't really mean anything. It's just a measure of variance, okay? And then I'm going to add them up across the 4 cars. All right? So what does 9.237 mean? I can't tell you. It doesn't mean anything. It's just a number that kind of is this abstract representation of how dissatisfied people are, or how, dissatisfied, because the higher the variance, the more dissatisfied they are. So then I'm going to go in here, and I'm going to solve this, and I'm going to say, all right, I want to minimize this number, whatever it is. I just want to minimize it by changing these cells. So just like in the traveling salesman problem, I'm looking for an order, right? And I'm going to make them all different. So I hit solve, and let's see what happens. So just a random arrangement of 1 through 16, which is really considered random because it's an arbitrary index to each person. So this is really a random arrangement. Has 9.237. Let's see just how good we can make it. So it's grinding through, and it says, okay, oops, what did it do? Jump back. I don't know why I jumped back on that one. Maybe I'll turn it off so I don't have that problem. So let me go back in here and solve and see what happens. So it's grinding down, and it says, okay. So what happened? 9.62 went down to 4.57. So I cut that variance roughly in half. Okay. Now let's just do an eyeball test. The term is interocular trauma test. I mean, you just kind of look at something. Let's look at it and see if the numbers make sense. These 4 people here, well, they all line up on music, pretty close on temperature, and on stopping, a little bit of variance. Here, they all line up on music, they all line up on temperature, and they pretty closely line up on stopping. And here, so looking at this, it looks pretty good. And it turns out that it's probably about the best you can do. So you may say, yeah, but I mean, you're putting a 3 with a 1. It's like, yeah. So, one of them likes to stop a little more, but they perfectly line up on the music and the temperature. Now, if one of these was a little more important than another one, you could create some type of ranking. So you could come in here, and let's suppose that the most important thing, which actually looks like it's pretty good here if you look at temperature, but you could come in here and you could rank these some way. So you could come in here and say, you know what, I'm going to make the temperature, well, let's make the stopping, I want it to be 3 times more important than music or temperature. Just take a 3 and multiply it, and then do it for each one of these. Okay. And pay attention to this example, because I believe at some point in your career you may be able to use this, it turns out. It's great for if you're presenting something and you're trying to show why you did something. And well, we ranked this a little more or less. And so do you see how we ranked this column 3 times? Now notice that this number went up, but it's an arbitrary number. It doesn't really have any real meaning anyway. So when I solve 9.63, I was able to go down to 7.4. So now these numbers, see how they're more in line with one another, and then these 2 metrics kind of paid the price. Okay? Why did I pick 3 times more? I just did. Why not 5 or whatever? So you can actually use this to create some type of ranking scheme to weight different factors. So let's just get rid of that. So does everyone see how that this is fundamentally a traveling salesman problem? I mean, is that clear? Let me just go back in and solve it real quick. Yep. know, we should be able to drive it down a little bit. That's kind of concerning. Did I forget to take one of them out?
Maybe it changed its mind.
Yeah, it looks like that I've is what? Oh, they changed their mind. Well, look, if you solve this, it may actually, it may actually give you different answers, but they may be, you know, this car may be different. No, there it is. You know, you're just basically saying these people are in the same car, but these four answers could have been down here. You see what I mean? There are multiple optimal solutions to this in terms of this ranking. So every time you solve this, you may not get 314, 314, 111. You may get 11, 1, 14, 3. But it doesn't matter. So if I come over here and do that, I type in, say, 11, 3, 14, and 1, okay? And I copy this and paste it in, it's going to be the exact same answer. You see what I'm saying? That this doesn't really matter of what ranking it's in. It just matters that it's part of the same group. And that comes from how I've set my objective function. So for this particular problem, there are many, many arrangements you could put these in, but it turns out they're going to be the same. You know, car 1 may be different than car 4, but what's important is that the same 4 people are in the same car. And that is kind of a function of how you develop the model, okay?
There's a different way of solving these, Donna. I remember last semester you showed us a problem for the dorm, like how many students want to smoke, how many don't want.
Right, exactly. So one of the problems that he's talking about is, and that's a little bit easier formulation, because what I was doing, like with the dorm problem, is I was putting people with 2. So the way I did it then is like this. Let's suppose you had a ranking. Let's suppose we have, like, on a scale from 1 to 10. You know, someone has an 8, and someone has a 4, and someone has a 2, and someone has a 6. And let me just do 4 people, and someone has a 4 here, and then this is like a 7, an 8, and a 1. And I have these 2 criteria. What I would do is take the difference between these 2. So I would take, like, this minus this, and I would square it, okay? And that is still a measure of spread. I'm just taking your value and my value, taking the difference and squaring it, okay? Well, why didn't I take the standard deviation? It's going to give me the same answer, because we're going to be, instead of mine minus yours squared, it's going to be mine minus the mean squared plus yours minus the mean squared, okay? So, you know, when you're dealing with 2 people instead of, say, 4, I would just use the difference. So I would just take, like, you know, this person's 1's value minus person's 2's value and just square it, because that ensures it's always positive. But that is still a measure of spread, if that makes sense. And by squaring it, it's always a positive number. So it forces us, what you're trying to do is you're trying to find some function that causes the difference between 2 people or between 3 or 4 or 10 to be as minimal as possible. So if you're dealing with, say, 3 or more, you probably want to use like a variance or standard deviation function. If you're dealing with 2, it's just simple to square it, okay? So then the question becomes, well, let's suppose that instead of having 16, that I had like 800, and I was trying to put them, say, you know, 6 to a group or something like that. You know, how would you do this? Because I manually had to do each one of these. I couldn't just drag it. That's where you might get in and use your Visual Basic skills of writing a little script to assign functions to each one. It's always great if you can figure out how to kind of drag and drop or so like if I highlight these, do 2 of them, will it allow me? No, it doesn't allow me to do that is the thing. It doesn't allow me to just drag them down. So I actually had to manually go in and write these. But if I had a really large problem, I would figure out some way to where I only had to do this once, and then I could highlight, drag these down, or use some script that would write those in for me. Okay, and then that's just exploiting some type of other skill that you may have. Okay, so that is how you would solve this problem, and there's all different variants that you could use. Okay, is it clear what the traveling salesman problem is used for? I mean, you could sit around and come up with an infinite number of variations and how to, solve. One problem that is actually used at large college campuses where they specifically, use this is scheduling of classrooms to classes. At Bluefield State, we're small, it's easy. We just always teach OR in this classroom, okay? But when you get to larger campuses where you have large student bodies and many buildings and different professors, you put in those constraints, and there's an optimization algorithm that goes in and will grind maybe all night on this and actually create the schedule for the whole campus. So that's why you may have to take a class across campus and move back around. So this is, it's something that's actually done. For us, it's pretty simple. But when you get, we had a lot of students and a lot of faculty and a lot of different classes and a lot of different classrooms, you have to have some help with that. All right. If there's no questions, then basically make sure you review the lecture and the problems that I go over in the lecture itself. Okay.
Is this next test we're going to have the final, or are we going to have a separate final?
We will have a separate final. Yeah. So we'll have 2 more tests.